So welcome everybody, and first of all, let me say thanks to the rector, to the decan for this very nice word. I mean, it's really very nice, all what you said. And also I would like to thank you and our institute and many colleagues, because the reason why today I'm here for my Antrittsvorlesung is because I really had people trusting on me and giving me this possibility. And I hope that I will, do good and that everybody will be happy, basically. And I'm very happy to see this audience, that so many people are coming, and I'm also happy to see that many students are coming, because for me, this is really the heart of my job at the moment as professor. Besides research and besides, of course, community service, it's also very much important, the relation with all of you, with the students. So, and now I want to start a little bit with my topics. And so this is an Antrittsvorlesung, so it will be really a Vorlesung. I will try to explain in a very general way few ideas that we try to develop in Innsbruck in the group of ultracold atoms, with Rudi, Hans Christoph, and Florian. And thinking about a title that could somehow summarize my work over the last years, I start to think that actually particles likes to organize themselves. And so, and they have really a natural tendency to build up structure, or to build or to pack together. And so this was somehow some idea, and then some idea got more clarified thinking about one paper of an Italian physicist. Okay, of course I'm Italian, and so very strong connected with all the physics history in Italy, which is Ettore Majorana. So Ettore Majorana disappeared at the age of 32. And in a very mysterious circumstance, and people also, there are many people that do not really trust that he's died or that he disappeared, but this was not the topic. So he wrote already at 32, 9 scientific papers, plus the 10th one, the last paper, that was about some, let's say, topic in between social science and physics. And actually the title was this, The Value of Statistical Laws in Physics and Social Science. And basically he recognized that there are, very big similitudes, so that there was some similar, let's say, guideline in between really social life and physics. And he recognized that in both domains, so it cannot happen that an event is just a result of a fatal succession of phenomena. Always statistical laws are governing how things develop and how the life develop and how the physics develop. And this was the idea that really the basic law governing elementary phenomena, but also social science, have a statistical character. And this was really, maybe now it's sort of pretty straightforward to think about this idea, but this was the base of econophysics, And in quantum physics, thinking about statistical properties, we have just two kinds of, let's say, macro, class of particle. The one which we call boson and fermions, they follow different statistical laws, and they are extremely different. So we have the bosons, as quantum particle, and the fermions, which if you think about having them at 0 temperature, how do they organize in an harmonic trap? You see that they organize in a very different way. So the boson has all the tendency to occupy a single state, which is also the lowest in energy, while the fermions itself do not have at all this tendency, and they rather want to occupy one by one. And so all this comes from the idea of the symmetry law of the wave function. So one is symmetric under permutation of position, and the other one is antisymmetric. And from this fact, all the statistical laws are completely different. And putting together the idea of social life, it means that, boson will build up a society in which everybody not only want to stay together, but they also want to do the same things. Fermions, on the other hand, are very, let's say, independent-minded objects. So they all want to do, so they know about the existence of the other, but everybody wants to do what they like to do. Okay, so now you can think about in our society what's the mixture in between these two kind of class. And if you think now about quantum gas, there is a very specific way to see the problem. And here the really relevant quantity is the de Broglie wavelengths. Okay, so the de Broglie wavelengths, it was at that time a revolutionary quantity or parameters to introduce in the system, because what tells you is something about the duality between wave and particle. And so this basically is the extension of the wave particle. And it's dependent of the temperature, so lower is the temperature, larger is the de Broglie wavelengths. And this also means that this is a criterion to define classical gas and quantum gas. So the basic idea is that when the mean separation between two different atoms is in the order of these de Broglie wavelengths, then the system starts to acquire really a quantum behavior. And of course, now at this point, the particles feel their difference, whether they are boson or fermions. And so if they are bosons, a quantum gas can do Bose-Einstein condensation, and you see how do they distribute in a very narrow peak when they are released from an optical trap. And if they are fermions, there is a Fermi sea that gradually emerges. So they gradually start to occupy one by one the different state. But of course, I mean, all this is related to the idea that you have to produce an object which is at ultra low temperature. But what means ultra low? I mean, it's very hard to get a feeling in general for us in our daily life. And so it's good to think about order of magnitude a little bit. And to do this, we have to use the temperature scale introduced by Kelvin, because he also introduced an absolute zero temperature, which is here. And now, at room temperature, you are roughly here at 300 Kelvin. Here, it's the conversion between Celsius and Kelvin. Now, I mean, in our day life, what we would define hot? For sure, summer. And in the atmospheric, I mean, highest temperature ever measured was almost 100 years ago in Libya. So they reached almost 60 degrees, so very hot. And the coldest one, on the other hand, do you know how much can be the coldest one in the Earth? Minus 20? No, it's nothing for an Innsbrucker. Minus 80, yeah. Here we are. It's roughly, it's a little bit higher, it's almost minus 90. And this was the Voskov station in Antarctica in 1983. So you see, from here to here, it's passing to the situation of cooking eggs on the sun to really be basically frozen in this condition. And between these two extremes, there is only a difference of 150 degrees, okay? So this is definitely not the kind of difference we are speaking about with quantum physics. So now, what is hot? It's easy to understand, because you can think about, for example, the temperature of the sun's surface, and here you know for sure that it's very hot. Now, if you want to go to the other extreme, so here nearby the zero scale, and you want to enter in the quantum physics, you don't have to use the linear scale, because it would be complicated to visualize. What you have to do is the logarithmic scale. And now in the universe, I think that the coldest place in the universe is the nebulosa Boomerang, which is about 3 Kelvin. But quantum physics, so the temperature that we reach in our lab to study quantum physics, is here. So it's not, so remember, in between the Libya and the Vostok station, it was only 150 degrees of difference. Now we speak about temperature which are 9 orders of magnitude lower than the temperature where we live today. So something really extreme. And it's here where really quantum physics start to appear. And of course, I mean, you can have so once you produce a quantum gas, you can think to study, I mean, the quantum gas using 2 different points of view. Either you study the few body physics, so how 2 particles interact, 3 particles interact, 4 particles interact, or you can approach the many body physics, in which you can have very spectacular effects like the Bose-Einstein condensation. This is a phase transition. So for some specific value of temperature and density, what you get is that all the atoms will occupy a single state and will produce this big peak that I've showed you in a slide before. So this is how it looks like, let's say, our machine to go to this ultra cold temperature. And all the physics basically happens here. So nowadays, I mean, the first Bose-Einstein condensate has been produced in 1995. And nowadays, I mean, we know very well how to do. The sort of the technique might have many differences, but somehow they are also pretty general. And what you do, you start with a piece of metal. Okay? And to go to ultra-cold temperature, you should heat up the piece of metal. So first of all, this looks like counterintuitive, but you need to produce a gas. So you need to heat up a little bit. In the case of erbium, which will be the example I will give, you have to heat up at 1,200 degrees. And then what you do, you use laser light to cool the atom. I will not explain how these things are done, but it's really the instrument are laser light. And laser light, again, a different one to trap your atoms. And you can have all your atoms or your little ball in an harmonic trap. And then you can do what is called evaporative cooling. So you decrease the height of this potential, and you let the hottest atom escape. And the other that stay will collide and rethermalize to a lower temperature. And then, of course, very important, it's also to try to probe. I mean, we have to see the density distribution and how our atoms behave. So you, again, use usually laser light to probe your atoms. So this is the periodic table. I mean, a very important point is, OK, can we produce Bose-Einstein condensate of each of these species? So, of course, the answer is not. And actually, I mean, I think that only 10% of this diagram have been explored so far. So we have more than 100 atomic species in our periodic table, and roughly 20 or 25 are unstable, so are radioactive, so you cannot use it. I mean, hopefully nobody wants to use it. And then, but then the other, I mean, many species, I mean, are unknown in terms of how laser will cool these atoms, and also a little bit unknown the scattering properties. So far, I mean, initially, so there were all atoms so the atoms from the alkali, so the group 1 atoms, which have been Bose-condensed. So the first one was in 1995, as I already mentioned, the first one, and as you can see, so they were all alkali and all made in the United States. So now the things, I mean, comes a little bit more colorful. So people moved from the alkali to also other systems, but also to go on with alkali. And also more, let's say, nations start to play this game of Bose-Einstein condensation. And those are all the Bose-Einstein condensed atomic species we have so far. And I have to say that this Innsbruck has really a world record, because it's the only city in the world that was able, for the first time, to condense 3 different atomic species for the first time. And those are cesium, strontium, and now erbium. And yeah. You know, when you put in Google the flag of Tirol, also the flag of Linz came out. And I was close to make a big mistake. Yes. OK, but let's go on. And so I will tell you a little bit the story today of erbium, and I will tell you a little bit more about the story of cesium, but more related to which kind of physics you can do with cesium. And actually, in our, let's say, consortium, our group, which, I mean, is led by Rudy Grimm, so we have many different experiments. Actually, we have 7 different experiments with use different atomic species. And this is because, I mean, they want also, so we also want to access different kind of physics. I will mainly focus on the cesium lab, which I serve as co-PI, and then I will tell you about something about the new project, which have been funded with the ERC, so with the Institute money, first of all, and then with the ERC and the START grant. But I will just flash. I will not enter really in the details of the physics in a very specific way. I just want to give you a feeling of what we can do in our lab. And this is how, I mean, the machine really look like. This is the erbium machine. So the piece of metal that you have to heat up is here. And then here, this red part is really the high temperature oven. So everything is heated up, and then you have an atomic beam that starts. And how this is how it looks like then. Let's have a look. So you start. So this is the oven. And then the atomic beam start. Here it's a transversal cooling, so you use cooling light to slow down the atoms, and not really to slow down, to collimate the atoms, which would start like this. Then the atomic momentum in this tube, I have to speak fast, this tube, and they get slower down by again some light, and this tube is called Siemens lower. And this is really the heart of our experiment. This is the science chamber where we produce the magneto-optical trap, and then we compress this magneto-optical trap, and from here there are all the other steps. So here more or less we are at microkelvin temperature. We need to go to nanokelvin. And so you can also really see the moth by eyes. I mean, this is a normal picture, and this is the atomic clouds, which are trapped by the light and the magnetic field here in the moth region, the magneto-optical trap region. And for the animation, I have to thank Albert that really, I mean, helped me a lot with all these things, and he did completely this animation of the moth chamber. And now the next step, as I told you, is to put in another, in a trap. I mean, at this point, you have the atoms which are already cold, but you need to trap it in sort of an harmonic trap, for example. And then here, you have to do this evaporative cooling. Basically, you lower the depth of the potential, you let the hottest atom escape, and the other to thermalize. And after this, you start to do this evaporation, and more you kick out the hottest atoms. If you do it in the right way, and I will not explain what this means, what you get is this really prominent phase transition from a thermal gas, which have basically a Gaussian distribution, to, I mean, a Bose-Einstein condensate, which have a very narrow and high density peak, which have a Thomas Fermi distribution. So this is the fingerprint, I mean, or let's say of having a Bose-Einstein transition and Bose-Einstein condensation. And once you are here, after a big effort, because it's really not trivial to build all this apparatus, really, I mean, the fun sort of start. And so here you can start to do really quantum physics. And you have two different points of view, or two kind of class of effect that you can think about. One is few body physics. And I will speak a little bit about the few body adventure in Innsbruck with the result given by the left lab where Rudy is the PI. And I will tell you also a little bit, I will just flash a few ideas about my new project, which is this erbium project. So let's speak, now it comes a little bit maybe boring for some of you. And so let's think about what's the difference between few body and many body physics. So now if you have two balls and these two balls collide, you always think that this problem can be solved, both in classical physics and in quantum physics. Okay, it's not surprising to you because, I mean, it's simply two balls that collide. But the way it's solved, it's quite surprising because at the end, if two particles are far away, then they arrive, they collide, they do something at short range which depend on the way they interact, so on the short range potential. Then you would expect that once they get out, they remember which kind of interaction they had at short range. And the answer is not quite. Basically, after a collision of two particles, if the particles are in the ultra-cold regime, after this collision, the only thing that they get, basically, is a phase shift. So they are exactly the same wave function which describes the two particles with a phase shift. And this phase shift, the limit of the phase shift for momentum that goes to 0, so this delta is the phase shift for two-body collision, give the definition of the scattering length. So basically, it doesn't matter which kind of potential you have here at short range. The only thing that matters is which phase shift you get at long distance. And this is basically already some idea of universality. So if you have whatever potential, but then at the end, given two different potentials, the phase shift is the same, then you don't care about potential. So, and then in ultra-cold collision, everything is described by a single parameter, which is exactly the scattering length. And so all the complicated potential that it's very hard to calculate, I mean, in two-body physics can be calculated, but it's very hard, can be completely neglected at this stage of two-body physics, and you can simply think that it's a contact potential with some constant G, which is the, let's say, a coupling constant. So pretty surprising. Doesn't matter what happens at short range, in two-body physics, all what you need to know is the scattering length. And what about many-body physics? Okay, so the situation can be much, much, much more complicated, but somehow you have also, I mean, an easy way to think about the problem, because if you have many particles and you are in the ultra-cold temperature, and these particles are also dilute, that means that they can collide only by a binary collision, so two-body collision, then there is a very straightforward link between a two-body collision and many-body collision. And so you can see this as, again, in terms of phase shift, and you can use an approach which is called the refractive index approach. You have your particle, and this goes in an atomic medium. And then you want to know the wave function after passing this atomic medium. And the kind of collision this particle can do here are only binary, so only two-body collision. And then what you would get after some easy math is that the wave function that describes your final state is equal to the initial one, again with only a phase shift. And again, a phase shift, you can think about a change in momentum due to the fact that the particle moving in this atomic medium can be accelerated or can be decelerated. And so this is the meaning of your phase shift. And the phase shift is again given by the scattering length. And then you get this potential, which is at the basic of the contact potential with the coupling constant, which I've described before. Now, the situation gets more fascinating when it's not only a many-body problem, but also you have a Bose-Einstein condensate. And here, what you have to do is to describe, I mean, the behavior of the Bose-Einstein condensate with a unique, let's say, macroscopic wave function. You cannot divide anymore one particle and the atomic medium. You have to consider a wave function which, let's say, include all the particles which are in the Bose-Einstein condensate. And here, what you get an equation which is very similar to a Schrödinger equation, normal Schrödinger equation, but with a nonlinear term, which take in account to the potential with this coupling constant that we have defined before. This equation is named the Gross-Pitayevsky equation, and have been derived independently by Gross and Pitayevsky, I think, in 1961. And I'm really proud to say that this was at the basic of many, 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 let's say, development in cold physics. And I'm proud to say that Pitayevsky today is here with us in the audience. He came just today from Trento for a collaboration with Rudy. So thanks to be here. And also I have to say that there is also Sandro Stringari and Lev Pitayevsky, together with the Trento theory group, have been really, from the beginning, the driving force to understand ultra-cold matter. I think it's pretty fair to say like this. So I'm very proud and honored to have them here today, both. And but then, I mean, at this point, I mean, from what I've said, it's like, okay, so you understand two-body physics. In some way, in some condition, you also understand many-body physics. And I mean, then it would be easy to understand three-body. I mean, if you understand many-body, for sure you would also understand three-body physics. And here the real problem comes, because the answer is no. So the simple problem of having three balls and what happens during a collision of three balls, you cannot analytically solve this problem. Sounds incredible. We can do many fascinating things in physics, but the simple point is how three balls or three particles collide, you cannot solve this simple problem. And here it comes really the field of few-body physics. And it's a very general field, of course, because few-body systems are everywhere. So you can have it in nuclear physics, for example, the triton, which is basically one proton and two nucleons. This makes a three-body system. And you can have it in hollow nuclei, so particle physics, nuclear physics, with very different energy scale. And few-body physics is also very relevant to ultra-cold atoms. Look, here you have in pico-electron-volt energy, and here you have in mega-electron-volt, although they share similar problem. Okay, completely different energy scale, completely different size. Here we speak about something which is a femtometer or something like this. And as I told already, it's not analytically solvable, but I mean, that's not the end of the story, because we need to solve this kind of problem. Then we have to add some approximation. We have to test our approximation, and we have to understand really how to tackle this problem, how to treat three-body problem. And it's, as I said, it's in general, there is no quantum, so there is no general solution to the quantum problem, but there is a special situation where a quantum, so a solution exists. And this is the Efimov result, because he found a solution to the three-body problem. And so that's why I use a title that Rudy also likes to use. It's the mysterious Efimov quantum state. So this is the group that have led all the experiment I will show you, and this is our theory collaborator. So now, three-body problem. So the situation that Efimov had in mind, for which he found really a solution, is the situation in which you have three particles here, and that they interact resonantly. So the interaction is extremely strong between these two particles. It's resonant interaction. All the pairwise interaction, I mean, are very strong, which means that the scattering length is much bigger than all the other scattering length, the other lengths in the problem. Here I have introduced the van der Waals length, which is the length after which you define, let's say, it's the range of the potential. So here we would say that it's a short physics, short-range physics, and you don't know a lot about this, and it's very hard to calculate short-range physics. And here, at least in the two-body case, you can have an analytic potential that describe this, which is the van der Waals potential. Okay, in this situation of a resonant pairwise interaction and the universal regime, so Efimov found this very counterintuitive solution. So that these three particles can bind together and form a bound state, which is a trimer. Okay, maybe it's not very, let's say, exciting if I say like this, but if I say to you, it's not only one state that they can produce, but an infinite number. And if I tell you that there is a relation between one three-body state and the other one, and if you consider one, the next one is 22.7 times larger, and the next one is 22.7 larger. Here, the factor is only 2, because 22.7 means that you take Italy, you multiply by 22.7, and you get Canada. So it's really something, I mean, beside the Italian, that will remain how they are. And yeah, so this was really some very strange solution to the three-body problem, the existence of this infinite series of three-body state. And actually, the community really took this solution with skepticism, and many theorists have tried to disprove Efimov, but at the end, they all find a different way to prove it. And so at the end, everybody was convinced that actually, I mean, the Efimov effect was true, but somehow it was called a new pathology for the three-body system. It's like the three-body system has a disease, is sick. So it was considered something extremely special, I mean, almost a theoretical artifact. But now, having a little bit a look more on what Efimov was predicting, one has to look about how this tremor state, what's the energy of this tremor state, how do they organize? And so now, so let's consider two particles. So here you have zero energy. Let's think that this is the energy of two particles. And then two particles have also, I mean, in the positive scattering length range, there is also the solution for a dimer. Now, the Efimov scenario is in the three-particle sector, and this is how the energy of this Efimov state appear. As I told you, there are infinite many states. As I told you, I mean, there is this scaling factor, which is 22.7. And it's not only that the size changed by 22.7, but also the binding energy. So from this one to this one, it gets 22.7 square times more loosely bound and so on. But it also means that if for some value of the scattering length you find an Efimov state, then if you multiply by 22.7, you should find another one. But here there is also something which is again very counterintuitive. And this says that in this region, I mean, two atoms cannot bind together. I mean, here, two atoms can bind together, and this is the blue line. So it's the bound state for 2 atoms. Here, 2 atoms cannot bind together. But 3, yes. And this is called the Borromean state because of the symbol of the Borromean family, in which you have basically 3 rings. So 2 of them are not connected, and you need the 3rd one to connect it. So you have many examples of Borromean system, also in nuclear physics. I don't go into this, in which, I mean, you have, let's say, halo nuclei, in which, I mean, the nuclei itself is much larger than what would be expected by the simple law. I mean, and the first one was lithium-11. But I want to show that also in social life you have a Borromean state. So what's an Efimov trimer according to Woody Allen? So an Efimov trimer, according to Woody Allen, is this. Now, I don't know how many of you saw this movie, which is Vicky Cristina Barcelona, but the take-home message is this one, is that as soon as one of these went away, the other 2 could not bind together anymore. So this is a Borromean trimer. And coming back to our scenario, what I want to say here, it's that, I mean, this Efimov state have been predicted 35 years ago. And actually, 43 now. And for 35 years, there was no experimental evidence of the existence of this Efimov state. And the reason, it's very simple, because as you see, I mean, this spectrum is a discrete spectrum, in the sense that if you have a 3-body system and the interaction has this value, between, I mean, the scattering length has this value, nothing happens. You really have to have specific value of the scattering length. So you have to have a way to change it. So now, in nuclear physics, there is no way to change, a really not easy way to change the strong force between neutron and proton. In halo nuclei, the only thing you can do is to change the mass to slightly change the interaction between these 3 particles. But with ultracold atoms, really what you can do, it's you have a very easy way. You change the magnetic field, and this is easy to do in the lab. And what you do, you completely, I mean, can completely access continuously, basically, let's put in this way, all value of the scattering length that you want. How it comes, this is also an idea coming from nuclear physics, and this is the idea of a Feshbach resonance. Now, this is something for just 2-body physics. I don't want to enter in the detail. I want just to say that if you change the magnetic field, you can change the scattering length. And you can change the scattering length from positive to infinite through a pole, and then again to minus infinite. I mean, of course, plus and minus infinite, you don't access this in the lab, but in principle, and to any negative value that you want. So basically, we have something that we can easily control in the lab that can allow us to access all the interaction. And so then it's pretty easy to access, I mean, this Efimov scenario in principle. And this is like how the Feshbach resonance look like in the case of cesium. And this is only to say that cesium is particularly well suited to change the scattering length, so to change the interaction between particles. It's a particularly rich system in this respect. And so the way you probe, then it's simple. I mean, you just look at how 3 particles collide. And when you reach, I mean, this crossing point between a trimer and 3 free atoms, what you get is a resonant enhancement of losses. I mean, and this resonance enhancement of losses occur with a period of 22.7. So this is how to do. You take your atoms and you probe here. It's simply lifetime. You look at the atom for different time, and you see if you have, I mean, an increase of decay for a given value of the magnetic field. And this was the first evidence that we got in Innsbruck. This was the first ever evidence of an Efimov state after really 35 years of search in many different systems. And as you see, this very prominent increase of the decay rate, this is really the signature together with other, but this is the main signature of an Efimov state. And after this observation, I mean, many things happens. And if we put together, here was the original prediction from Efimov. As you see, for 30 years or more, everything stayed pretty quiet. Then a couple of theorists I mean, made very important work because they found a connection between Efimov physics and ultracold atoms. So basically, they understood that ultracold atoms can be really the right place where to look for Efimov physics. And it's roughly here in the year 95, 99. And here was the first Innsbruck observation. And the year 2009 was also very important for Efimov physics because many, many experiments have shown this kind of physics. So it seems that it's not something special to cesium, the atoms that we used in Innsbruck, but it's something which seems to be intrinsic to any ultracold system. So it's not a pathology, but it's something really intrinsic. And here it's more or less the moment in which I arrived in Innsbruck. So it was really an excited time because it was the rising up. So it was very nice, really, to see how the field developed and how people get more and more interested in this kind of physics. And so during my time, I mean, in Innsbruck, we have done, many, many publications related to Efimov physics. Of course, I have not the time to speak about all of this, but I want just to point out, 3 publications very fast, very shortly. And I will start with this one, which have been defined as the bombshell PRL from the Innsbruck group. And has been defined like this from Chris Green, which is one of the pioneers, really, of the field. And why it's a bombshell, it's pretty clear, because we already mentioned about 22.7. So the distance between these two states is well defined. So the relative energy is well defined. But nobody tells you where this series starts. So this point where the series starts, it's unknown. And this is given by the so-called 3-body parameters. Now, if you change these 3-body parameters, of course, the spectrum change. And before our work, the general understanding, it was that the 3-body parameters, which I define here as with this symbol A star minus, was something dirty. So all the dirtiness of short range was all inside these 3-body parameters, basically. So you cannot calculate it. You can say almost nothing about this because it's really a full system-dependent parameters. It's short range, non-universal. So there is nothing you can do about this. These Efimov states are universal, but it's not universal the point where these states start. So this was the general understanding of the community. And then, we said, OK, we have cesium. In cesium, we can really tune the scattering lengths, and we can use different Feshbach resonance. This means using different Feshbach resonance means that we can access the same range of the scattering lengths, which is our universal quantity, using different resonance, meaning changing the short-range physics. Basically, in using this resonance to tune the interaction, or this one, what we change is only the short-range physics. But since the 3-body parameters is dominated by short-range physics, we should find the Efimov peak at different value of the scattering length. No, if everybody was right. There was some debate. I cannot enter in the detail. But this was our idea. And what we found is this. This is the original observation in 2005. And those are the other observations that we got, in 2010, 2011. And now, if you put all this together, you see that all these Efimov peaks really occur at the same value of the scattering length. So the 3-body parameters do not depend on the short-range physics somehow. Or if it depends from the short-range physics, it depends in a very loosely way. And if you plot the position of this peak, you see that over an Efimov period defined like this, it's not important, you almost see no difference. And what you have to do is to magnify this scale really to see a little bit of difference. But I have to say that within, 2 sigma, all these points seems to be one on top of the other. OK, now it seems that it cannot be a coincidence that whatever you do, you change your magnetic field by 1,000 Gauss, and you find always at the same value of the scattering length the Efimov peak. So it's not a coincidence in cesium, but then the second question, is it in general a coincidence that for some special reason cesium behaves very nicely? And actually, we find out that no, that this is very general to the other system. And then we find out this thanks to, many discussions with other groups. So now, what we found, and also suggested by the lithium group, is that, the 3-body parameters it's almost always 9 times minus 9 the van der Waals length, so the range of your potential. So this is the range of the two-body potential. This means that if you know well your two-body potential, and I want to remember you that the two-body physics you can solve, then you can completely model the universal three-body system. So you have both the van der Waals length and the scattering length, which are two-body quantity. You know everything about three-body system. And this was really, I mean, I think, a major contribution that we gave into the field. And then, of course, the next question is, what happens if instead of having 3 particles, you have 4, 5, 6, 7, and so on? I mean, is this a strong universality? Will also go to larger and larger system? And this was our question. I mean, we moved from 3 to 4, and I want just to flash a few ideas. Because, I mean, originally in 73, there was a paper that said that there is no Efimov effect for, I mean, 4 or more particles. So in principle, you don't have to have this kind of physics if you consider not 3 particles, but 4. But actually, I mean, there are really brilliant theorists around. And one of the very interesting paper was about the possibility to have, for each Efimov state, which is a 3-body state in green, 2 4-body states which are attached to the 3-body state. So as soon as you basically get 3 atoms to bind together, nearby, also 4 atoms would bind together. This was, I mean, and this was also pretty, let's say, counterintuitive. And the paper has been, let's say, published in the 26th of April 2009. And they also took the old Innsbruck data from 2006, and they claim somehow that the existence of the 4-body state was already evident from this original 2006 paper, and basically considering these 2 points. But of course, for us, we thought, okay, maybe we need a little bit more point to really prove something. And we went really for a dedicated experiment triggered by the discussion and by the idea of this theory group. And so now simply the take-home message is that, yes, these 2 4-body states exist, and we could really see, I mean, we could really get the fingerprint of this 2-body, in this 2 4-body state, and we could also measure the 4-body collisional rate. This was the first time that the collisional rate involving 4 particles have been measured in the experiment. And for the expert look at the unit, it's a little bit unusual. And these end up with the paper which have been published 20 days before the theory paper which proposed the experiment. And these are, let's say, stuff that sometimes happens. Very nice. And yeah, and of course the next question, okay, for 4-body physics, maybe can you have 5-body physics? And there is really a brilliant physicist, young one, that was working at GIL and the group of Chris Green, and this is Javier von Stecker, which got the Diamond PhD prize in 2009, and he predicted that you don't only have a tetramer state, so a 4-body state, but you have also a 5-body, a 6-body, a 7-body, a 8-body state, all connected to the initial Efimov state. As soon as you get this one, you get all an infinite family of universal clusters which are really attached to it. So this was really the idea. I mean, in experiment, it's impossible really to get signature of very high order collision. I mean, because it's really the probability that 6 particles get together at the same time. But we gave a try for n equals to 5. And actually, we saw something. OK, we have also better measurement, but this was easy. So we saw the trimer state, we saw the 4-body state, and we saw the 5-body state. As you see, the signal gets smaller and smaller, and we stop here. But this is really a major conceptual advance. And now to make a joke, this is an example of mathematical induction. Because somehow, so you want to prove the existence of universal cluster state connected to an Efimov trimer. You prove the statement for the lowest n, which in our case is n equal 4. Then you prove it for n plus 1, and then you can say that it's valid for any n. So this is a little bit a joke, but the take-home message is that like this Efimov physics is like a domino physics. As soon as, you make one of these domino cards fall down, all the other will fall down. As soon as you take out one of these n-body states, I mean, all this universal picture will break down. So they are all tied and connected one to the other, from 3 to 4 to 5. And it's enough to know what happens at the two-body level. And so now, I mean, the conclusion of this part is like that 42 years ago, the Efimov physics was a pathology of the three-body system. And now what we know is that it's almost everywhere, sort of. This is exaggerated, of course. And it can be in 3 identical bosons. It can be in 3 non-identical particles. It has been observed with fermions. And also in particles having different mass. And so I can use, I mean, the word of Efimov to really say finish this part, where Efimov said that on a personal note, I well remember the time when the giant tremor made outstanding physicists raise their apron. It has been heartening to witness to the evolution of this miracle to quantum mechanics from questionable to pathological to exotic to being an hot topic of today ultra-cold physics. The fairy tales is becoming a reality. And this is Efimov that came to visit us in 2009 in Innsbruck, and we were really proud to have him and to show him what an ultra-cold experiment looked like. He was surprised, I think, a little bit. And let me now, in the last couple of minutes that I have, really to flash in, I cannot enter in the detail, on the, on the youngest experiment in the ultra-cold group in Innsbruck, which is the erbium experiment. And so what we did here, basically, so far was to produce an ultra-cold sample of erbium, and we were able for the first time to Bose-condense this atomic species. And this atomic species is very, let's say, exotic. So the story a little bit of our lab started in 2009, and at that time so the group were pretty small, and it was the time where Johannes Denschlag, maybe some of you know him, he left because he got a position in Ulm as professor. And so, I mean, thanks to the support of the Institute and, of course, of Rudy, I got in heritage, I mean, let's say, in legacy, his lab, but, I mean, also Albert. And this was really very nice, and we started with him. And then things developed because I mean, all the funding initially were from let's say, the Ultracold group and from the Institute. And then I got the start prize, so we could really, I mean, speed up the experiment. And then the tables start to enter from a Windows. The group start to increase a little bit. And here it's really, let's say, the starting that I would define the starting. When the optical table enter in the lab, it's the starting. And I got the ERC starting grant, so this was also nice to have more funding. And now, this is now the erbium machine. We got the first BEC the 8th of March 2012. And this is the team today. And why? So why we want to produce this erbium BEC, Bose-Einstein condensate, is because, I mean, so far all the physics I've explained it to you, it's really coming from contact interaction, which is a short-range interaction, as I told you, and it's isotropic. So it doesn't matter whether the particle is here, 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 here. I mean, the interaction itself is isotropic. But now you can make, I mean, the things even more, let's say, exciting if you consider a more special interaction type, which is this kind of anisotropic interaction. So the only way to introduce this long-range anisotropic interaction in the system is to have the so-called dipole-dipole interaction. So it's long-range because, as you see, it's dependent on space, R. And so it has a long-range character, so the two particles will feel each other also when they are pretty far away. And then it's anisotropic because it depends on the angle. This means that it makes a difference for the particle whether they are here or here. Actually, they will attract like this, and they will repel in this direction. And so, of course, you introduce in the system a new ingredient, basically, which is anisotropy. And this changes completely all the properties. So a classical way to think about this is normal magnet. Now, if you have two magnets, I mean, and you have the sud pole, and you try to get them together, you are not able to do this, okay? So even though they are not touching, they feel each other. So this is the concept of long range. And the concept of anisotropy is that if you do like this, they cannot touch, they repel strongly, but if you turn it, then they can attach. So this is the idea of anisotropy. And we can do it with two different systems, with using an electric dipole moment, like in polar molecule, or magnetic dipole moment, like in magnetic atoms. And in Innsbruck, we have both experiments. This is an experiment led by Hans-Christoph Nagel, which I also partially participate, and I have no time to say all the nice results that the experiment got in the last years. I will say a little bit about erbium. So erbium is really a very exotic class of atoms which have not very much explored in ultra-cold atoms. So there are many reasons why this is very exotic, and especially it's the electronic configuration. I mean, already the electronic orbital distribution is very anisotropic. So all the scattering and all the properties, not only due to the dipole-dipole interaction, so not only due to the high magnetic moment, but also due to how the electron clouds, organize, are very anisotropic. Actually, it was a good idea to work with lanthanide, especially, if I would work in economy, because the price of, for example, dysprosium in 1 year doubled. So we should have both kilograms and kilograms of erbium. Unfortunately, we just bought milligram for making quantum physics. And, but if you're interested, it seems that the trend will go on, and you have lanthanide in all your smartphone. And so what is a nice example to explain? I will not explain the quantum physics. I want to explain the classical physics. It's really ferrofluid. So ferrofluid is a special fluid which have a lot to do with liquid crystal, which have been studied a lot by Pierre-Gilles Desgennes. And so it's some fluid that it's a fluid, but simultaneously have some crystal properties. So you know that the fluid do not have any shape, okay? So it's a fluid. It's like, I don't know, like water. What's the shape of water? It's the shape of the container. But then you have situations which are in between being a solid and a liquid, in which, for example, you have liquid crystal, in which due to the interaction and the anisotropy, you can really build a structure without having a container. And these are the ferrofluid. And so I will show here what the ferrofluid is. So if you can see here, this is, and meanwhile, I just sent a video, very spectacular also. So you can choose. If nobody look at me, I will simply stop. No, so this is the fluid itself. You can see it here. So this is here, this fluid. And now if you, so this really, it's normal fluid, okay? And if now I put some magnet and I make the magnet be closer and closer, what I see here, it's the appearance of one peak. Then I get closer. So there is no container so it's simply, it's simply doing this because it's following the magnetic field. And if you do more, you have more and more. Okay, so it's not so easy to do this, but you can have more and more and more. And if you have a lot of time, you can do this kind of structure, which, of course, we didn't have in our lab. But now I want to show you that actually this structure that you see here, this kind of peak, you can see in ultra-cold atoms. For example, atoms like erbium, strongly magnetic, erbium, dysprosium, chromium, can really build a natural, this kind, not really naturally, but with, a very small action on the system, they can really build this kind of structure. And I show you a very nice image of the first, this is the D-wave collapse. This is the chromium atoms. So they are in an harmonic trap, and when you increase a lot the dipolar interaction, you see that the system is called to collapse or to produce a D-collapse, D-wave collapse, and they start to build naturally this kind of peak structure. So this is the quantum equivalent of a ferrofluid. But of course, since we are in quantum, there are also much more other things that we can do. And in our lab, erbium lab, we also saw the same kind of feature. And this was the first, for us, the first proof that our condensate, not only it's condensate, but it's also strongly dipolar. And I don't want to enter in the detail, but there are many, many, many proposals regarding what you can do with the dipolar system. And actually, what you can create is sort of some, let's say, particle that move in sort of a floating lattice, and this lattice itself is created only by the interaction between the atoms or the polar molecule. And this brings me almost at the end of my talk. And many of these ideas and many of the things we are thinking in the lab to do with our dipolar system are triggered by also the close collaboration with theory group, like, for example, the strong collaboration that we have with the solar group. And many of the members which collaborated with us are now in the audience. And so I think that this also means that in Innsbruck, we know how to build a quantum society somehow. So we have a very strong, institute, which is our Institute for Experimental Physics. And our institute is really connected to the Institute for Quantum Optics and Quantum Information. And we have also very strong connection with all the physics department and all the institute in physics. And we really share ideas. And we have also instruments to build our quantum society. And our instrument, for example, are the new founded SFB grant from the Austrian Science Foundation, which is called Foundation and Application of Quantum Science. And another very important instrument that we have is the Innsbruck Physics and Research Group, which is led at the moment by Rudy. All these make a very strong consortium for physics, and for what regard, my specific scientific interest, a very strong consortium from quantum physics. And so I think that we are a very good example of building a quantum society here in Innsbruck. Don't ask if we are boson or fermions. I don't know, we should see. And with this, it's the moment of thanks. Of course, I thank all the members here, which makes very enjoyable, fruitful my work in Innsbruck. And I have to thank really all the secretary staff and the workshop member, because they are always very important. When you have to build up a new experiment, they are really super important. And so I want to thank them, and I want to thank also all the members of the Ultracold group. It has been great to work with all of you, and thanks a lot. And I want more specifically to thank the three teams, which are the rubidium cesium team, the left team, and the erbium team, that really were like the team with whom I have collaborated more closely. And finally, Rudy speaks always in German with me. Now I speak in Italian. Grazie, Rudy. Really for your support. Grazie means thank you. Danke. I think it's easy to guess. And really I want to thank you for your great support over the last 60 years. And of course I want to thank my family, my father, my mother, Peyo, and my little kids which are here. And I want also, let's say, my last thanks is really related to the person which really convinced me to do physics. He's a physics professor in Naples. His name is Antonio Barone. I think that Lev knows him. And he passed this way just 1 year ago. And for me, it was one of my mentors for many years. And I want to thank him and his way of, sorry, this is a little bit from thinking about physics. And with this, thanks. And that's it. Thanks.